Howdy and welcome back. So let's continue today's lesson by going and exploring some of the implications of storing a collection of objects within a contiguous block of memory, as our VectorInt did with a dynamically allocated array on the free store. So VectorInt, we built this up the previous lesson. We added in maybe a couple of extra functions, but the interface is more or less shown within this UML diagram, as is the data members. We had a pointer array, which simply pointed to the dynamically allocated array object that a specific VectorInt object owned. Size referred to the number of slots available within that array that were currently being used, while capacity was denoting the overall total number of items that could be stored within the array. So if you recall, the pushback operation would essentially increment the size of the array by 1, and we could continue pushing back integer objects into our vector event as long as the size was not at the capacity. In the case where size did equal capacity, we had to perform a resize operation to make room for the object that we would like to add to the vector of integers. For this type, we defined a single constructor. It was parameterized and took in the size of the dynamically allocated array that we would go ahead and allocate, as well as a initial value that we would like to have each of those objects started out with. We said that the initial capacity would be 2 times the size, and that we went ahead and would define a destructor to go ahead and free the dynamically allocated array at the end of an object of this type's lifetime. We had 2 getter functions to return the size and capacity of a VectorInt object respectively, as well as a definition, which we did not show, however you could complete on your own, of an overloaded subscript operator to access a specific element within a VectorInt's dynamically allocated array. Finally, we defined the pushback operation and went into a little bit of detail as to how the dynamic resizing of array would occur. So we'll go ahead and just refresh this here briefly and pose the question, well, how difficult was it to push an integer object to a VectorInt object? Well, if size was not equal to capacity, this was as simple as adding the value to the open position, which was effectively communicated to us by the size data member. Remember, because of zero indexing, size told us the number of elements within our array. So in the case of this diagram here on the left, the size would be 1 because 1 element is residing there. However, because of zero indexing, that single element resided at index 0. And the next available index where we could add an element to would be at +1 to 0, or the value stored by size. In addition to this, and the new kind of spin on this diagram for this lesson, is that we are showing the whole capacity of the array, albeit a little bit grayed out as to show that it is there, but it is not currently in use. So looking at this array here, we can see that only this portion is currently in use. However, we have all of this available to us. So if we were to push back the integer value of 1, with a focus on the size of capacity, 1 would be added at the index size. So in this case, slot 1 is where 1's added. And at this point, size is equal to capacity. So the next instance is, well, if we'd like to push back an additional integer object to this array, some sort of resizing procedure is going to need to take place. Although we covered this in detail, I think it's beneficial to briefly look at it here. So how difficult was it to push back an integer object to a VectorInt object if size was equal to capacity? Well, we went through the definition of a resize private member function for our VectorInt, which would handle the resizing process. And then we defined an additional private member function grow, which was responsible for actually growing the array twice its original or current capacity. So in the case that size is equal to capacity, the first step in the process is going to be to grow that array. Thereafter, we can simply add the value to the open position and increment size by 1. So if we run through this, picking up where we left off on the previous slide, we have the case where size is equal to capacity, and we'd like to push back an integer object integer value of 2. So in this case, a resizing operation is going to occur before that object is going to be added into our integer array. We can see that here. So we went out because size was at capacity when we grew that array by the original capacity times 2. So now it has a capacity of 4. Notice here we haven't added anything just yet because the first step in this whole resize process is just getting us this array. After we've had it, look, we've got now 2 available spots where we can go ahead and add some value to. In this case, since we were in the pushback procedure and we wanted to add in this integer value of 2, it will be pushed back to the array, effectively increasing the size of that array by 1. Now notice here, if we look at size, the size has shifted from 2 to 3. And look, the cool thing about zero indexing here is that the next available slot where we could push something back to this array is going to be at the 3rd index. So we can use that as we're going through this process. So before we get into, I guess, the more interesting considerations for this component of the lesson, let's just think back here and recall that arrays are created to be a specific size. If they're on the free store, we do have the ability to essentially resize them. But remember that this procedure gives us a brand new array, and we have to essentially copy over the old data from the previous array into the new array at the corresponding indexes. And we'd have to do this every time. There's no ability to simply tack on at the end because that memory on either side of our array could already be in use. Therefore, we need to ask the free store manager for a brand new array. We perform that copy, deallocate the memory associated with the old array, and take our pointer and point it to that new array. So what if we wanted to expand the behaviors provided by our VectorInt type to allow us to push to front? That is, what if we wanted to add an object at the 0th index of the array, but we wanted to preserve all the data that was originally in that? So in order to push front, the idea would be similar to kind of push back in that we'd add somehow to index 0, and all of the values that were previously at 0 to size -1 would be shifted up an index. So we're going to go ahead and consider the case where size is not equal to capacity. We're going to set up an array that is going to have an available position open where we could have pushed an object back into. However, this time we're going to push something to the front of the array. I've changed the representation of how I'm going to show these diagrams simply because it's a little bit easier to work with to illustrate this process using one. So here's an array, and we can assume that this is an array owned by some VectorInt object. And currently it is of size 7, so there's 7 elements within it, and its capacity is 8. We can see the index is shown in the top row in bold with the value at the corresponding index showed in the second row here. So we can see that we have values at indexes 0, 1, 2, 3, 4, 5, and the slot 6 is currently available for us if we wanted to add something into this array. So we wouldn't have to resize. We can add a single integer object pretty much anywhere without having to resize, though the operation and procedure for this will be a bit more involved than simply pushing to the back. So we want to implement this push front. So at the end, we would like to have, if we were pushing, say, the value of, I think I picked 11 to the 0th index, 3 would need to be moved into the first index, 9 would need to be moved into the second, so on and so forth, such that room is created for 11 at the front. So if size isn't equal to capacity, we're going to move each element up 1 index. We're going to add an element to the open space created at array of 0. So let's focus on the first step in this operation here first. We're going to move each element up 1 index, and I'm going to start at the top end of this and move the element residing in index 5 into index 6. You can see here that 9 was moved into from slot 5 to index 6. Notice here I'm showing that this position is open by simply graying out the previous value that was there. The reason being is that C++ is not going to zero out any memory. And what we have did here was simply copy the value at array of 5 into array of 6. But for all intents and purposes, please think about this as, that space is completely open now. There's nothing in it, and we can put something else there. So let's go ahead and continue this process and see what happens. So the next thing we need to do is 5 needs to be moved up from array of 4 into array of 5. So let's go ahead and do that. So we can see here 5 was moved up from its previous position into this new one. And we now have a new space here. And we can see 5 is sitting pretty at array of 5. So again, just think about that as opening up this space at index 4 for us. And now we need to continue this process and move 7 into array of 4. So we go ahead and do that. And you can see how everything's slowly being shifted up one index at a time to effectively open up the space at index of 0. So we continue this process. Again, think about slot 3 is now empty, and we can go ahead and move 4 there. Continuing this process, slot 2 is now empty. Again, we can think about it as such, and we'll move 9 up there. At this point, we're going to open up the position at array of 0. So here we go. Think about that as open to some value, and let's go ahead and move 3 into it. Now at this point, if we look at this, index 0 of array is now open, and we can put in some sort of value that we wanted to push to the front of this array. In this case, again, assuming this is open, I believe the element we wanted to add, I was right, it was 11. So notice here that in order to add at a specific position within an array, we essentially have to, from that index forward, shift everything down to open up a space so that we can drop in the value that we would like at that position, in this case, 11. So again, look at the number of kind of assignments we had to do here to actually make this happen and move things across and create that opening at position 1. And again, that's because we're dealing with a contiguous block of memory. And if we wanted to say, if we were at capacity, we can't just run off into, say, the lower end. So we can't go this way to like array -1, because that's probably being used by something else. And doing so, that operation is undefined. And we can't go out that way either, because again, we have no clue what is on either side of this array in memory. And this gets fun even further, because we are dealing with a fixed allocation of space. And at this point, size is equal to capacity. So on the next operation, we'd have to go through this whole, we'd have to get a new dynamically allocated array and iterate through this current one, copying the old values over to the corresponding index in the new array. And then, I mean, there's more efficient ways to do this, but let's say we were adding at position 0, you could obviously accommodate this during the copy process, but still, somehow, in order to add into a specific location in the array, some shifting has to be done to open up the space for that value. Now, this one's a little bit, more straightforward. So what if we wanted to expand the behaviors provided by our VectorInt to allow us to now perform a delete at a specific index? In this case, let's say we want to remove the element residing at index 3. So again, just look over here and keep in mind what's kind of happening here. Size is equal to capacity, right? What we're going to want to do here is effectively decrease the size by this array by 1 in order to free up a space and perform the deletion of the object residing at index 3. So how we go about this is going to be how you've probably presumed. So notice here's the initial configuration. To perform the delete, we're simply going to overwrite whatever's at that position with the value at the index above it. So whatever's in array of 4 is going to get copied into array of 3. And the idea is that if we're deleting, say, the value at index 3, we need to fill that gap because this is contiguous memory. We can't just like chop this up and do something with that and do something with that and then piece it back together. No, instead, we unfortunately have to move everything at the upper end down one index to fill that gap. So let's just, I like to doodle, I'm sorry, but let's continue that. So let's get this back into the state. So we're looking at closing out that one. So 7 is going to be moved there. This will effectively create an open position at slot number 4 or index number 4. We'll go ahead and copy that residing at index of 5 into it. We'll continue this process. Okay, we have a slot open now at array of 5. We'll go ahead and copy that to array of 6 into it. And at this point, everything's been shifted down 1 to actually perform this, this deletion of the value at index of 3. And to go ahead and reflect this, we can see that the top end is now open. All of the original data, minus that which we wanted to remove, has been preserved. It's still in there. And finally, to show that we have a newly open position within our array, we can go ahead and decrease size by 1. And remember, C++ is not zeroing out any of the memory. So I'm showing here that 9's still kind of there, but the second we perform a pushback or another operation to extend the size of this array by 1, that space is going to be reclaimed and used for something else. So again, for all intents and purposes, simply think about that slot as being open and readily available for an integer value. So some observations through this process. It's very fast to get an item in a list. We can simply use point arithmetic, and if we want like the third element, or sorry, the element residing at index 3rd, we can jump there directly by simply adding on to the array's address the size of an integer multiplied by 3 and dereference the result. So we're able to jump there directly and just pull that object, this object here, out at our will. The other observation is that these arrays are fixed size. So if we want them to grow, we're going to have to perform and actually implement some sort of resize operation. I mean, this is really fairly straightforward, but it is some computational cycles we'll have to use towards this. We've also noticed that it's pretty slow to insert at a position that's not at the end of the array. And again, that's because we have to shift everything up in order to open the location to make the assignment at. Likewise, it's relatively slow to delete an element because we can't just simply chop it out and stick together the pieces on either side of the element that removed. No, instead, we actually have to perform this downshifting, which will again effectively decrease the size of the array by 1, opening up an additional position at its top end. So with that in mind, let's we've kind of considered this vector event. Let's go ahead and move into this idea of a sequence of nodes and see what that's all about.